All right, everybody, welcome. Today we're going to be talking about enzyme mechanisms. This is a third of our 4 topics on enzymes. You can see we have the group arrangements up here. So today we'll be talking again about enzyme mechanisms. Thursday we'll be finishing up our discussion of enzymes with enzyme regulation. And then next Tuesday we'll be moving into carbohydrates, followed by nucleic acids. So we'll have 2 lectures on nucleic acids, 1 on nucleic acid structure, and then 1 on nucleic acid function. Now you'll notice today, and also on Thursday, you'll be getting PowerPoint handouts. So the format for the end of second half of enzymes and carbohydrates, it's going to be a little bit different from what we've done before. It's going to be more PowerPoint based, but with interactive aspects. So it'll be a little more blended and a little shifted a little bit from group work, where group work is still a thing, but it's not the only thing that we're doing in class. Okay, so you guys will notice you've gotten your quizzes, your quiz regrades and your exam ones back. So, as some of you have already pointed out to me, I am in fact fallible. I make mistakes. But when I have people find things on their enzyme or on their exams, I like it to proceed in an orderly manner, so I don't have a long line of people running up with me to nitpick their points so they get a 90, okay? So, there's an exam regrade request on the Sakai. I will be uploading the key this after class, by the way. There's an exam grade request form. What you can do then is you'll fill out the form if you notice there's an error. Now, what I will say, if you find an error that's in your favor, I will not blame you for not saying anything. You bring it to my attention, of course I'll correct the record. But whether or not you choose to point that error out to me is another thing. Now, if you turn in a regrade request to me, I do reserve the right to look back over the whole exam. So if you find an error, maybe take a look back through the rest of the exam, see if I missed something else perhaps in your favor, see whether or not it adds out. So if you're feeling pretty good about your exam and your score, but there's something that went a little wrong, but you think that you'd still get the same grade plus those points, if I regraded it, turn it back in. But proceed with caution before you turn it back in. Now that being said, I'm not going to be some angry avenging angel, but it's only fair that if you hand it back to me that I take a skim throughout the whole thing. Now, I will be accepting regrade requests. I ask that you turn them in by Thursday. So that way I can turn them back around over the weekend and get them back to you Tuesday. So, and that also encourages you to take a look over it now while it's still fresh, rather than dragging it through. But again, I recognize I make mistakes, and so I want a channel by which you can communicate that to me. But without one, that puts me in a weird spot. Okay. So again, we have our dope sick assignments due Sunday at midnight. So we're reading through chapter 1, where hopefully you started reading, but you're learning about some of the corrupt aspects of the drug industry. And, and for me in particular, I listened to this as an audiobook when it first came out because, like all great things, I heard about it on NPR on Fresh Air with Terry Gross. I bought the audiobook, I listened to it while I was doing my experiments this summer, and I was just totally shocked. And it changed the way that I thought about addiction, especially specifically opioid addiction. And funnily enough, last week on Fresh Air with Terry Gross, she interviewed someone else who just wrote a book about the neurochemistry of addiction. And actually that person was a professor at Furman when I was there, but she's moved on to Bucknell now. But anyway, Fresh Air with Terry Gross, lots of great things coming out of that podcast. But this is not an ad for NPR, this class. Okay, but either way, I'll be really interested to see what you guys have to say and then how that'll come into play when we do a class discussion of a paper on the structure of an opioid receptor. So the structure of that receptor, one of those receptors in our brains that opioid molecules actually bind to and then trigger pathways in our brain. Pretty cool. Take-home quiz, again, will be assigned on Thursday. The way this is going to work is I am going to upload either a Word document or a PDF of the exam. You will download it, you will complete it, and bring it to class on Thursday. I guess if you wanted to do it over email, you could also email it to me too, but I will leave it up to you. It needs to be turned in, I'm going to say by the beginning of class on Thursday, unless I put a different deadline in the syllabus, in which case that supersedes it. I should probably check that. But either way, it will be due Thursday. And you can email or hand it out, but it will be downloaded. I will not be handing out a paper copy. Exam 2, March 7th. And then lastly, we have a help session on enzymes tonight. Again, that's to this week. That happens to be the night that works for me. On Thursday during class, I'll talk around and see if there will be any interest in having a session next week as well. And then finally, today, in addition to changing up our format, we're going to be a little bit truncated, seeing as now I've been yammering for 5 minutes. We'll have class for approximately 40 minutes, at which point Dr. Anita Colley from the Teaching and Learning Center will be coming, and she'll be doing an activity to talk to you guys about how you've been learning in this class so far. So I'm really curious to see if the ways we've had the class set up has been beneficial to your learning and to learn about how that has been or hasn't been working for you. So, but Dr. Anita McCauley will tell you all about that, and she can do a much better job than me. But just so you know, she's coming, so don't be alarmed when she pops her head in or when I go out and fetch her. Okay, before we get started, do we have any questions? Yes. So you can order it. There is a pleasure copy in the library, and then there is a reserve copy in the library as well that's been ordered. So there are 2 copies. I also have a copy that I would be willing to lend out to somebody in a dire circumstance. But yes, so I also do have a copy. And if you need help with that after class, come talk to me. Also, office hours will proceed as normal. So after Dr. McCauley's done, I will pop back in, take any questions, rearrange the tables per usual. Oh yes, and about one thing I will say about the exams, overall, they looked pretty good. The average, they looked good. The average was an 86. The low grade wasn't that low. I was not really concerned about anyone's performance on this exam. Everyone has set themselves up to where they should be able to do well for the rest of the semester. Okay, nobody's dug themselves into a hole. What I will say though, if you did score below an 80, I would say maybe set up an appointment and we could talk about strategies for studying for the next exam. That's what I will say. But other than that, yeah, again, the average was 86. So good job, team. Okay, yes, and we had a question. Yes. Okay. Actually, that's some question I haven't thought about. You know what? Email me. I'll say, just send it to me and send me the Word doc or the PDF in an email. I like to see it click. I like to see these things click in my mailbox. I know that means 21 emails, but I'm okay with that. Yes, Maddie? Okay. Yeah. How do you do that? I won't write it on my hand. Do that. Actually, while I'm thinking about it and while I'm talking to you guys, would you be interested in doing a review section next week as well? Okay, all right. Then I will send a doodle poll, and I will not set it up. I will not set it up so I have something going on in a separate window and it doesn't send like last time. But next week, I'll take a look at my schedule. There'll probably be a little bit of self-filtering going on with the dates and times available, but I will send out an email for next week. Okay, any other questions before we get started? All right, let's launch into the wonderful world of enzyme mechanisms. All right, so you guys watched 2 videos about enzyme classes and enzyme catalytic strategies. Why did I make you do that? Well, because as you walked through the videos, it was short, relatively cut and dry. And for me, I'm more focused. You need to memorize them. You need to be able to identify them. I'm concerned about you being able to apply them to various enzymes that we see in class, which is what we're actually going to practice today. We're going to go through, we're going to see some mechanisms, and I'm going to have you do some applications. Okay, so today we are going to focus on types of enzymes called proteases. Now, based off the name protease, does anybody have an idea what a protease might be doing? What might a protease's job be? A hint is that we've already talked about 2 proteases, chymotrypsin and trypsin. Yes, Elena? So it's breaking a bond, but the name of the enzyme hints at the type of bond that's being broken. Yes, Grace? Yes. So these are enzymes that are protein enzymes that are chewing up other proteins. And actually, I realize I have that right there on the slide, and that these enzymes are going to be enzymes that are going to catalyze the hydrolysis of peptides. Now, as you remember from memorizing the roles of the different ones we talked about for peptide sequence, different enzymes are going to have different specificities. Now, serine proteases hang out in are synthesized by our pancreas, and they go like into our stomach where the pH is really low. And in our stomach where we've synthesized these, because if you guys remember from when we talked about amino acids, what's a big source of, where do we get a lot of our protein in our body from? Where does it come from? Thinking back to just the most simplest definition of a protein. I'm sorry, I don't have chocolate to throw at you today. Where do we get our proteins from? Okay, so essential amino acids. Where do essential amino acids come from versus non-essential amino acids? Yeah, so it comes from our diet, so it comes from food. So we make these in our pancreas. They're secreted, they hang out in the acid in our stomach, and they help us digest the proteins down in food. Now, serine proteases get their names from the fact that all of these enzymes have an active site serine residue that is responsible for the majority of the chemistry. And so when we walk through a serine protease mechanism for chymotrypsin, we're going to see that serine is going to be playing the starring role. You could also imagine, by extension, that there might be other enzymes with amino acids that look like serine that perhaps might play a similar role. Now, as you can imagine, proteases, kind of might be a little bit dangerous. You don't want to just, if we were to have proteases and just unleash them into your bloodstream, they would chew up everything in sight. And we don't want all of our proteins to be chewed because we wouldn't have any hair, we wouldn't have any skin, nails, whatever. So there needs to be some kind of a protection system in place to make sure that proteases don't go wild in our body. And so for this reason, we actually synthesize proteases as inactive precursor proteins called zymogens. So a zymogen is an inactive precursor to a protease. So in this case, and we can identify zymogens by the fact that they end in -ogen. So chymotrypsin -ogen is the precursor of a zymogen or precursor for chymotrypsin. So, and the way that zymogens are activated is you have another protease come in and chop it up. So if we have chymotrypsinogen, trypsin comes in, and trypsin is the enzyme that recognizes arginines and lysines. So trypsin goes and it finds arginines and lysines, particular arginines and lysines in chymotrypsinogen. It makes a chop between an arginine and an isoleucine. Two segments, and then after, so then we have one form called M-chymotrypsin. So that's one active form of chymotrypsin. However, it turns out that, and once we have the pi, it looks like an M, but it's a pi, the pi chymotrypsin can also be further processed by active chymotrypsin. And then, once you remove those two pieces, you can get the alpha active form of chymotrypsin. So essentially, what you need to know is, if we just had proteases running wild around our body, it would be, in layman's terms, an absolute shit show. So nature has built in these protection mechanisms to make sure proteases can't just go wild and chop everything up. The protease processing is found all over our body. So it turns out that trypsin is a nexus of this protease regulation. So trypsinogen would be the zymogen for trypsin, could either be chopped up by its product, trypsin, or an enteropeptidase, but then trypsin can go and activate chymotrypsin and also elastase. So all of these proteases are interrelated, and there's this network where they all kind of work on each other under the favorable conditions. Okay, so chymotrypsin. So again, to remember, what chymotrypsin does is it cleaves peptide bonds C-terminal to phenylalanine, tyrosine, and tryptophan. And so here we have the structure of chymotrypsin, and then we have a diagram of the sequence of chymotrypsin. And this is actually mature alpha chymotrypsin. Now, what I'd like you to do is I'd like you to look at chymotrypsin with your group, and I want you to come up with how many subunits does chymotrypsin have in the alpha form. All right? So take a minute, take 2 minutes, talk about it with your group. Okay, I'm just talking. If I didn't know any better, I think you guys wouldn't like each other. Okay. Would one of my groups like to tell me what answer you guys came up with? Of course you would. Anyone? Bueller. Remember, you guys do have roles. Reporters. Yes, Emily. You said there was 3. Okay, and I would agree with that. So the precursor to chymotrypsinogen has 1 chain. But when you chop it up, it gets 3. So in theory, you could say it had 3 subunits, although the A subunit's really small. Either way, there are 3 separate chains. So if you were to treat this with disulfide or with beta-mercaptoethanol to break up those disulfide bonds, you would see 3 bands on an SDS-page gel. Whereas if you just unfolded it and didn't add beta-mercaptoethanol, it would show up as 1. Just want to take a minute to reinforce some of the concepts we've learned in previous chapters. Yes, Elena. Yeah. It would break up all of them. It would break up all of them. It loves all disulfide bonds. Well, I guess it would really just depend like how long you treated it. But if you blast it with heat, so if you when you heat, you're putting it at like 80 degrees Celsius, which is well above the thermal transition midpoint for most proteins. You blast it with heat, you're throwing an SDS page. The point is you're blasting that protein. So, and if you're blasting the protein, it's unfolded. It's going to like all the disulfide bonds. So now, as promised, we are going to dive headfirst into mechanisms, and we're going to look at the mechanism for chymotrypsin. So, the overall reaction. All right, so we remember chymotrypsin likes big flat aromatic amino acids. And so if we have a protein where, so R is going to be connected to our N-terminal fragment, and R prime is going to be connected to our C-terminal fragment, chymotrypsin comes in using water as another substrate, and it's going to break apart that bond and add water across that bond. Or you could think of it as adding 1/2, or you could think about it as adding the 2 halves of the peptide to water. Both ways are correct ways of thinking about it. So before we dive in, there's a couple key steps that we're going to see in the mechanism. So first things first, we're going to see the serine hydroxyl acting as a nucleophile. But then, as a result of the serine acting as a nucleophile, we're going to see a tetrahedral carbon intermediate. Then after the tetrahedral carbon intermediate forms, that'll break, something will leave, and we will see an acyl enzyme intermediate. Then, once we have the acyl enzyme intermediate, we're going to have water act as a nucleophile and attack that central carbon. We'll see a second tetrahedral carbon intermediate, and something will leave again. So when you're going through and you're studying, if you're trying to memorize this mechanism or get it to a point where you could be able to figure out what happens, this slide should be your guide on how this reaction proceeds and the key parts that you need. Okay, so just a really quick review. All right, so if you're fearing nucleophile, electrophile, and freaking out, tonight or next week is your time to come talk to me about it or make an appointment, whatever is best for you. But before we get started, does anybody, and I was going to ask, but the definition's up here. A nucleophile is going to be a molecule that's going to, or an atom attached to a molecule that is going to be very electron dense. And so because it is so electron dense, it is going to want to share those electrons with the world, or a molecule that happens to be right next to it that's in desperate need of electrons. So nucleophiles, very often, they either have a negative charge on them and they want to neutralize or get rid of that negative charge because they happen to have an extra pair of electrons, and so that's the case of an O-, like you'd see a deprotonated hydroxyl, like you'd see on the end of a serine. Serine proteases, or a negatively charged sulfhydryl. So if you deprotonate a cysteine, it also has a negative charge on it. So in theory, a deprotonated cysteine or another sulfhydryl molecule could also act as a nucleophile. But it's not just limited to those, or those are the ones we'll see a lot. You can also see, we're not going to see any carbanions in this class, but the lone pair electrons on an amine can act as a nucleophile. We'll see that. So like if that's an amine on an imidazole, which happens to be a histidine, we could see that acting as a nucleophile, or we can see a hydroxyl group acting as a nucleophile. These also tend to be groups that might act as bases or donate their electrons to a proton. Electrophiles are atoms due to their arrangement in a molecule that are electron deficient. So they're going to want to be getting electrons from a nucleophile. And so these tend to be, we'll just go ahead and say carbons, but also sometimes a phosphate. They're going to be attached to other molecules that are much more polar than them. And because they're attached to molecules that are much more polar to them than them, those other molecules are going to be pulling away those electrons. So that's going to be priming these atoms to get those electrons from nucleophiles. So the most common electrophiles that we're going to see in this class, for now, are going to be C double bonded O's. Where do we see C double bonded O's or carbonyls? Anybody? Think about the mechanism of chymotrypsin that we're going to see in a minute. So it's the C-terminus, but also the carbonyl and internal peptide bonds. And then once we start talking about nucleic acids, we're going to see this happen with phosphate groups. But we haven't quite gotten to phosphates yet. But what's going to become really important in the second half of the semester. Okay, so enough yammering. Let's go ahead and see the main event, which is the mechanism of chymotrypsin. Okay, all right. So chymotrypsin, a really important characteristic of chymotrypsin is that it has a catalytic triad. And so what that means is it has 3 catalytic amino acid residues that do the chemistry. And the catalytic triad consists of, in this case, for a serine protease, a serine, a histidine, and an aspartic acid. Now, not all serine proteases or proteases are identical, so there could be cases where you could see these amino acids slightly switched up, but they'll still do the same job and proceed by a very similar mechanism. But for the one that we're learning about today, this is the catalytic triad. So if we look at our substrate, and again, our substrate is going to have, oops, I drew in, no, I didn't. Is going to have a phenylalanine, And if we recall, so N is over here and C is over here. And if we recall, we are cutting C to the phenylalanine. So we are going to be hydrolyzing. So we're going to be hydrolyzing over here, that peptide bond, that's C to the phenylalanine. So our catalytic triad, we're going to have serine, and here's where we're going to start to get lazy with drawing amino acid side chains. We're going to have histidine. Okay. Oh, histidine. Rats. Of course, I mess up my ring, and then it's going to take me like 15 minutes to erase the daggum thing. Okay. Yep, for sure. There we go. Yep. Sorry, guys. So sorry. There we go, pen. Okay. Okay. Here we go. And then finally, we're going to have aspartate. Okay. What's going to happen in this active site is, so we have serine acting as a nucleophile, I said. Now, that may seem weird because serine was not one of the amino acids we learned that has a pKa. But to some of you, I mentioned that serine has a pKa of around 13 normally, so it's not going to be deprotonated under normal conditions. However, in chymotrypsin, serine, that catalytic serine has a pKa of around 7. So, at physiological pH, it can be deprotonated. So how specifically is that going to happen? Well, what's going to happen here is the aspartate, the negative charge on the aspartate is going to be pulling on the protonated nitrogen on the histidine ring. And so what that's going to do is that's going to be pulling the electron density away from this nitrogen. Or it's going to be concentrating it on. So then what's going to happen is this nitrogen is going to become more basic, and then it's going to pluck that proton off of the serine. So now the serine is going to have an extra pair of electrons. It's going to be even more nucleophilic. So those lone pair electrons on the serine are going to make a nucleophilic attack on the carbonyl carbon of the peptide bond that is C to the phenylalanine, and those electrons are going to go up onto the carbonyl oxygen. So then what we're going to have is we're going to be seeing our first tetrahedral carbon intermediate. Our histidine is going to be protonated now. Our aspartate. Still pulling there. Whoops, okay. But now we're going to have our first tetrahedral carbon intermediate. And we call it the tetrahedral carbon intermediate because the carbon now, before it had a trigonal planar geometry, it had, it's planar. It had 2 things bound to it and 1 double bond with O, or had 3 things bound to it, so it's going to be planar. Now, when you get rid of that double bond and you have 4 things bound to it, it's going to adopt a tetrahedral geometry. Okay? However, oxygens don't particularly like carrying a negative charge. We saw that with serine. It wanted to get rid of it by attacking the carbon. So what's going to happen is that electron density is going to fold back down, but carbon can't be bound to 5 things. So something has to leave. Now, so what's going to happen here is this bond is the amide bond, C terminal, to the phenylalanine is going to break, And that bond between the C and the N is going to break. It's going to pluck off the proton from the histidine, and then that's going to leave. And so what we have, and by the way, when this happens, the amino acids around that oxyanion are going to be forming an oxyanion hole to stabilize that tetrahedral carbon intermediate. Okay? We talked about enzymes accommodating intermediates and transition states. That's an example. And what's going to happen is there are going to be some amino acids in space around that. They're going to have their backbone amine protons oriented towards that charge. Yes, Sydney? So these So it's not participating in like the attacking or even the acid basing, but it is helping to make the amine more basic so it can deprotonate the serine. Yes, so the aspartate is playing a support role. The histidine and the serine are doing the chemistry, and the aspartate, yes, is playing a supporting role in this. Okay, so now, I want to make sure that I'm not losing track of any atoms here. Okay, so we have our serine, our histidine. Our histidine's deprotonated again. Our aspartate still has that negative charge, is still pulling on the histidine. But then we have the second half of the peptide that's attached to the C-terminus of the original peptide. It's hanging out free. It's going to leave. It's going to exit the protein. So half of the original protein is going to exit the active site of the enzyme. But what we have here is the N-terminal half of the peptide is still covalently attached to the enzyme, and we call this an acyl enzyme intermediate. Because what we have here is the acyl, so that carbonyl is attached to the hydroxyl of an amino acid residue within the active site. Okay, so now the next thing that's going to happen is we're starting off with our acyl enzyme intermediate. So I'll redraw this. Oops. Yes, Sydney. Yes. The R prime half is leaving. You should say it leaves. Yes, you should totally say it leaves. Okay. All right. So we're bound to the serine. Okay, so we're covalently bound to the serine. We have histidine. Whoops. Okay. Sorry, guys. I apologize about the appalling state of my histidine. There we go. Histidine's deprotonated. Aspartate, obviously, deprotonated. And still pulling on that amine. I will post a cleaner version of this mechanism. I have it on a PDF, and I'll just re-upload it so you guys have a nicer thing to look at. So now we get to this point where the enzyme, oh no, I'm stuck, because it's literally stuck to its substrate. So what we have to do is we have to unleash that second half of the peptide so the enzyme can be back to its normal state, and also the thing can be chopped up. So we don't have anything else. We don't have any other amino acids that can do this job without getting even more stuck to the enzyme. So what the enzyme has to do is it has to pull in an unattached molecule to help break the enzyme from the peptide substrate. So it's going to use water as a nucleophile. So we'll draw in water. Okay, so we have water. That is water. I know it probably doesn't look like water, but it's water. So what's going to happen is we're going to see the histidine be pulled to action again. it's going to pluck the proton off of water, and then that will enable the oxygen on water to make another nucleophilic attack on that carbonyl oxygen. The electron density will go back up on that oxygen. The histidine now is going to be protonated. Aspartate, again, still looks the same. Aspartate's just still doing its job. Okay, so now we have what we call our second tetrahedral carbon intermediate. Because again, carbon down to 4 things, tetrahedral geometry. So what's going to happen is the same thing that happened the last time that we had a tetrahedral carbon intermediate. The electron density is going to collapse. However, what happens this time is if we're looking at our 2 possible leaving groups, we can either have water leave as a leaving group, or we can have a hydroxyl that's attached to a whole protein. Before, the second half of the peptide substrate looked like a better leaving group. But now, water is a pretty shitty leaving group. So what's going to happen is instead of water leaving, the serine's going to leave. So those electrons from the serine hydroxyl to the carbonyl carbon bond, it's going to break. It's going to pluck a proton off of histidine. And then what we're going to get is we're going to have the second half of our peptide substrate breaking free. It's going to have a hydroxyl group on it now. And then our enzyme active site is going to be regenerated. And so throughout this course, you're going to have to predict some mechanisms based off of what you know about other protein enzymes of similar structure. That's part of the job. But one of the things that's always important to remember as you're doing enzyme mechanisms is the enzyme always has to look the same after the last step that it did before the first step, because the enzyme always has to be ready to go to catalyze the next reaction. Now, that was a lot, but what I want you guys to do is I want you to work really quick in your groups, and I want you to answer these questions about chymotrypsin. I want you to look at your notes from enzyme classes. I want you to identify the enzyme class. And then I want you to pluck out any enzyme mechanistic strategies that chymotrypsin might be using, and we'll come back together as a class and point them out. Yes, no? Okay, but then you guys go through the mechanism and identify the class and the mechanism. Yes.
More than your class.
In theory, so like an oxidoreductase, something can be an oxidoreductase and something else, but only one's going to trump the other. Yeah, and I will post so that's going to be a free experiment. That's going to be an NH2 or the independent of you're taking one peptide and you're using water to break it peptide bond. And you're using two shorter. So it makes it. Yes. Comes out H2. Yes. Yes, strategy is the things that guys use in that reaction. I would say that would be examples of causes, yes. Okay. Unless you can find from the sequence. All right, guys. Oops. Okay, we'll pull back together now since we're running a little bit short on time. We will look at HIV protease on Thursday and finish with this. Okay, so what class of enzyme do we think that chymotrypsin is? One of my groups like to volunteer. Yes, or why would you think it would be an oxidoreductase, Kendall? Why did your group think so? Now, okay, so is there another group that came up with oxidoreductase, or did another group come up with something else? Okay. Okay, a hydrolase. And why a hydrolase? Okay. Anybody else? Anybody else come up with something different? And I saw a lot of groups, some groups had hydrolase and oxidoreductase. So there's a little bit of confusion. So in this case, this enzyme is going to be a hydrolase because it uses water to break a bond. I could see why if you were split between the two, you would put oxidoreductase first because oxidoreductase trumps other types of reactions, but this enzyme is not an oxidoreductase because although it's making and breaking covalent bonds, it's not making an exclusive electron transfer to the other. If you're going to be seeing an oxidoreductase generally isn't going to have to be doing, it's going where an electron gets or goes from one molecule to another. It's not shared in a covalent bond. And a key that an enzyme is an oxidoreductase is usually if it has a metal ion helping, or if it has a molecule like NADH, or a coenzyme like NADH or FMN, and we'll see plenty of examples of oxidoreductase. But I'm actually really glad you brought that up because, I mean, these enzymes, they are sharing electrons, it's just they're sharing them in covalent bonds rather than a direct donation. Okay, how about some mechanistic strategies? Don't be shy. It's okay. See, there's nothing. If you get it wrong, that's okay. There's no. It's okay. We're all here to learn. Yes, Kendall. Yes, general acid base. And so I saw some acid and base down on some people's sheet. And remember, acid base happens between a small molecule or water. General acid base is when an amino acid acts as an acid or a base. So general is what makes it different. So if you're talking about strategies to get full credit, you have to do general acid base. So we see, in this particular case, if we look to the first half of the reaction, histidine's acting as a general base here. Then histidine acts as a general acid over here. So if histidine's switching back and forth between acting as a general acid and a general base. How about another strategy? Yes, Janelle? Yes. So proximity and orientation. And I'll just go ahead and say proximity and orientation and transition state stabilization. Now, all enzymes use both proximity and orientation and transition state stabilization. But in this enzyme, I provided you a direct example with showing you how chymotrypsin has an oxyanion hole that stabilizes that negative charge preferentially over a double bond in carbonyl oxygen. So that's a direct example of transition state stabilization, and you could also argue proximity and orientation because it's helping to orient in the right way. Okay, and then lastly, were there any other strategies that you guys saw? There's one more. Yes, no? Yes. So this enzyme uses covalent catalysis. And we see covalent catalysis when we have the acyl enzyme intermediate, because the enzyme is literally temporarily covalently bound to its substrate. Okay? All right, so before I let Dr. McCauley in, do we have any questions? We will finish the rest of this PowerPoint on Thursday, and then we'll talk briefly about enzyme regulation. There will be pre-reading and a short assignment, but there won't be any videos. Okay, Hubert. With the I actually do like yours. But, I'm going to inherit, if Natalie doesn't want it, I'll take your china. And then we're also going to get Nancy's china. Which, Nancy's china isn't, it's not that it's ugly, it's just what you would expect Nancy's china to look like.